All right, so let's enter the analysis phase of this memory-hungry WCF service. Instead of waiting for users, for this leak to accumulate enough and kind of monitoring the process, we have a test app, and it's a performance test app that was written while the service was being developed, much like I showed in the previous module. And that test app is called perftest.exe. So I'll go ahead and run the application, and it's really pretty simple. Number of concurrent users, that's how many users you want hitting the service at the same time, iterations per user, and then you can do a start test, which will go and do put operations on the service, such as add book, or you can do get all books, which we'll call the get all books method of the service. So I just want to show, to start with, the memory consumption of this process. I'm going to use Task Manager to do that. I'll bring that up. And right now, as you can see, we don't have a w3wp.exe process, which is the IIS hosting process that the service gets loaded into. But what we'll notice is as soon as a method is being invoked on the service, IIS will automatically launch one of those processes. So let's just start with something simple. We do get all books with one user and one iteration per user. Here we see that w3wp.exe got started, and it's roughly at about 76 megs of commit size. And now we start seeing it go up. This is as it's processing that call to get all books. As a matter of fact, if I leave this going, then eventually it might run out of memory. If that operation breached the boundaries of the address space, or if it didn't, the call will return, but memory will not be reclaimed. So I'm going to go ahead and stop this actually, and I'll end the process. So that kind of shows you, gives you a good idea about how memory climbs as part of that method execution. Now, as we discussed before, we can have an operations engineer sit and watch Task Manager and then do a manual crash dump of the process. But a much more efficient way I'm going to show you is using DebugDiag. So I'll launch DebugDiag. And it gives us a few options for selecting a rule type. Now, what we're interested in is telling DebugDiag to take an action, and that action happens to be to generate a crash dump once the process has consumed X number of bytes of memory. To do that, we will use the performance rule. Capture user DUMs used to troubleshoot performance problems, including high CPU, deadlocks, and .NET memory issues. We'll click Next. And then we get a choice. What do we want to base our triggers off of? And since we're looking at memory, we're going to use perf counters, but you can also do it on HTTP response times. Right? That means, for example, take action if the response hasn't gotten back after X number of seconds. That's an example of that. But we'll stick with performance counters. We'll click Next. And here's where you can add the performance counter triggers. So I'll click the Add Perf Triggers button. And now you get to choose, much like perfmon, what performance monitors you're interested in. For memory, we're going to use the process, and we are going to select a counter called private bytes. If you look at the description of that, it tells you that private bytes is the current size in bytes of memory that this process has allocated that cannot be shared with other processes. Once we have private bytes selected, we can then go ahead and select which process. And as a matter of fact, I terminated the service process. So what I got to do here, I'm going to open up IE. I'm going to manually hit the service URL. That will then in turn cause IIS to load my service code into a w3wp.exe process. So that's now loaded. We go back now and see, let me do cancel here. Add Perf Trigger. Go back and do that again. We'll do process. And we're interested in private bytes. And now we should have w3wp.exe. That is the IIS hosting process that's currently hosting our service code. So I'll click Add and OK. So that's great. We now have a trigger, but we haven't really told DebugDiag what the thresholds are. So I'll double click this and I'll say take action when this counter stays above this threshold. Now remember, the perf counter is private bytes. That's the number of bytes. And what I'm going to do is say, well, if this process ever uses more than 150 megabytes, and it has to stay at that for at least a second or longer, then I want it to take action. So I'll click OK. We've now set the thresholds. Click Next. Now we add a dump target. So dump target is the process that you're interested in. So I'll say, well, the target type is an executable. It lists all the running processes in the system. So I'll scroll until I find our w3wp.exe down here. Click OK. Then I'll click Next. And here is where we get to tell DebugDiag what to do when that triggers. So I want to generate a dump, let's say every 3 seconds, that's fine. Start the timer, i.e. every 3 seconds when writing the dump file completes. And I want to stop generating after 1 dump. You can imagine, because this is an out of memory, so really chances are pretty good that we'll just need 1 crash dump, but imagine that this was some other issue where having a sequence of dump files X number of seconds apart would be a very useful thing. So you can set that up in this dialog. I also want to collect full dumps. That just gives us all the process memory. I'll click Next. Let's call this rule library memory issue. We'll click Next, and it asks if I want to activate it now, and certainly that's what I want to do. And the rule is running and it's active. It's now monitoring our w3wp.exe process. So let me now run our perf test again. I'll do the same thing, 1 user and 1 iteration per user, and I'll click Get All Books. I'll immediately switch back to DebugDiag and we'll see if this user dump count ever goes up. If it does, that means it's hit that 150 meg limit. And there we go, user dump count, 1. So now we know we got a good dump. And what I'll do now is actually go out and debug the dump. DebugDiag places its dumps under Program Files, DebugDiag, Logs, and then a folder that's named after the rule name. So if I just do a dir, we should see a, let's see, well actually it's called Perf Trigger Rule 1. If I go underneath there, we see that we have a dump file that was generated and with the extension .dmp. And now we can just use the debuggers. Oops, that's the perf test app that still has some issues. x64 ntsd-z to open a dump. We'll select the dump file that was generated here. Let's go ahead and open that. That brings up the debugger. And we do the usual kind of bookkeeping work. We fix up our symbols, we reload. This is a .NET app, so let's load up SOS. And let's just look at the state of the managed heap in general, just the overall size. So bang ee heap-gc tells us what the managed heap contains and the total size. At the way bottom here, we see that the GC heap size is roughly 66 megs. Now, there is another type of heap in .NET or in the CLR, and it's called the loader heap. That's where things like images, for example, .NET assemblies get loaded. To see the activity there, you can use the bang heap-loader switch. And I'll hit enter. And what we see here is that the total loader heap size is roughly 3 megs. Interestingly enough, if I scroll out, I see a lot of modules that are of size 0. I have no idea what that is all about yet, but it's probably not a good thing. So I want to find out in which particular application domain are these modules loaded. So I'll keep scrolling up, and we see here that it's for domain 2. So domain 2, you get some output like low frequency heap, JIT code heap, and then you get all of these 0 length modules. So I can get a little bit more information if I take the address of domain 2, and if I pass that to the command dump domain, followed by the address. This looks a little different. What we're seeing here, if I start from the bottom, that domain has an assembly loaded that's called some really bizarre name. The assembly prior to that that's also loaded some bizarre name, bizarre name, bizarre name. As a matter of fact, if I keep scrolling up, we have a ton of these in the process address space. Now, the one thing to keep in mind is if an assembly is loaded into an application domain, it will never be unloaded unless the application domain is also unloaded. So for all intents and purposes, all these modules that are named really bizarrely, we don't know what they are, they will stay in memory until this app domain is unloaded, meaning when the service is unloaded, and that is something that we don't expect to happen. So this is a potential problem here, right? Because if some of these assemblies, if they keep getting created and created and created, they're never going to get unloaded. It's going to grow and grow and grow our memory consumption. So a good clue here, right? This might have something to do with our problem. But we still don't know what these are. Well, there is. Let me go and pick one assembly at random here. Let's pick this one. 9VXHH-ZM. It tells you what modules it contains. And that module is also named pretty much the same name as the assembly. Well, we have the module address here. So we can use another command called bang dump module, followed by the address. And the output really doesn't seem like it's all that useful to us. It's got some attributes, assembly, loader heap. One key piece of information here is the metadata start address. If we were to dump out the contents of this pointer in character mode, and I'll tell it to dump from that starting address all the way up to the starting address plus the length of it, which is 4352, that will tell us the contents. Now, let me scroll up to the beginning here. This, yeah, I can't really get anything useful out of it. There's a GUID and some blobs, hash strings. That's probably the PE header. This is a bunch of stuff that I really don't know what it is. So I keep scrolling down, and then I start seeing what looks like XML. So open bracket, module, DLL, and then, wow, this XML serialization writer. As a matter of fact, DC book. So something with a book data structure is possibly being serialized. And it says Microsoft XML serialization, generated assembly. That makes sense. So it's a generated assembly due to serialization. And I can kind of continue looking through this, but at this point, my first inclination is, are we doing anything with the XML serializer class? So I'll switch over to the source code, and really I can just do a Control-Shift-F, which searches all files in the project, and do an XML serializer. And sure enough, it looks like we have we're using the XML serializer class. Now what function or what method of the service is this in? Scroll up, get all books. So what ends up happening here is that we get all the books in the database. And then for each and every single book that we've got, which is of type DC book, we serialize that into XML. And then we get the string, the XML serialized version of the instance, and we add it to a string array that we eventually return back to the caller. So what's wrong with this though? I mean, this is perfectly reasonable code. I'm just serializing instances of a particular and a relatively simple data structure. Well, this is a case where looking up the documentation, I'll go to Microsoft.com. I'll put in XML serializer. And I look at the documentation for that. And if I read enough, in the remarks section, there is a heading here called Dynamically Generated Assemblies. To increase performance, the XML serialization infrastructure dynamically generates assemblies to serialize and deserialize specified types. The infrastructure finds and reuses those assemblies. This behavior occurs only when using the following constructors. So if you use either of these two constructors, then the dynamic assemblies will be reused. So let's look at to see whether or not the constructor we're using matches any of these. So our XML serialization instance is based off of a type. That's the first argument. And then the second one is root, and root happens to be of type XML root attribute. So type followed by XML root attribute. Type, so either one of these, followed by XML root attribute, and that's none of these two constructors. Meaning that the other constructors of the XML serializer class do not cache the dynamic assemblies that they create. So every time you create a new instance of it, a new dynamic assembly gets generated. And this is what is the root cause for our long-term accumulation of memory. The more books you have in the database, the more serialization you'll end up doing, and the more dynamic assemblies will get created. Very classical example of an out-of-memory condition in a WCF service. Please do watch out for the generation of dynamic assemblies.